Okay, I'm going to get started. All right, so we have in the last lecture finished talking about calculus. We're going to start talking about um, differential geometry, and we started last time. So remember what we did last time. So the idea is that we're parameterizing sets by open subsets of locally convex spaces, okay? So the idea is you have a set, and I'm going to draw the set like it looks like something, some kind of surface or something. But of course, the kinds of things we're dealing with are potentially a lot more complicated than this. But to illustrate, so I have this set S, and I defined last time what I meant by a chart. Okay, so a chart took some subset, which I called U phi. Okay, and then it mapped it into some locally convex space, which I call V phi, by a mapping phi. Okay. And the only property here that phi had to have is that phi is a bijection from this subset of S onto an open subset of V phi. Okay, that's the only requirement that I had for a chart. So the interesting things start to happen when you start talking about multiple charts. Okay, so then we had this, so let me hatch this as I did last time. Okay. So if I have another chart, okay, and it had a domain, U psi, let's say. Let me hatch this one like this. All right. And so it has a chart map, psi, and it maps into some other locally convex space, possibly, V psi, and its chart, so its image has to be an open subset of the topological vectors, the locally convex topological vector space V psi. And then the interesting thing that happens here is that on the place where they overlap, okay, so the overlap here is going to map to by phi, first of all, to some region like this here. Okay, so that's the overlap. Okay, and then here it's going to maybe look something like this. That's the overlap. Okay, and then I had a mapping which went from this overlapped thing to this overlapped thing. And how did it do that? Well, it just went, I took a point here and I mapped it backwards by phi to a point in the intersection there. Okay, and then it gets mapped forward by psi into this overlapped region. And I know simply because phi is a bijection onto its image and psi is a bijection onto its image, the mapping that I get, which goes from this overlapped region into this overlapped region, which is psi composed with phi inverse, that mapping is definitely a bijection. Okay, just because phi and psi are bijections. But I have some additional conditions, and I wrote these down last time, so I'm not going to rewrite them again carefully. So there were two conditions. One is that the images of the overlaps had to be open in V psi, okay? And similarly, this one had to be open in, V phi, and this one had to be open in V psi, right? So these things, over double hatched regions down here are open. That's one requirement, okay? And then the other requirement is that the mapping, which sends this intersection into, or this image of this intersection into this image of this intersection, okay? That mapping had to be what I called a CR diffeomorphism, right? And so what that means is that the mapping itself is of class CR, okay? And moreover, that it's inverse. And so its inverse is just going to be it's going to be, of course, phi composed with psi inverse. Okay. That inverse mapping also has to be of class CR. That's the definition of a diffeomorphism. So it's a CR bijection with a CR inverse. And it's not true that a CR bijection automatically implies that the inverse is CR. That's not true. And there'll be some examples on homework to sort that out. Okay. All right, so that's kind of where we were last time. And so the idea is that this mapping, this overlap map, okay, so this thing was called the overlap map. Okay, that this mapping is in the class of differentiable mappings. It's a really nice differentiable mapping. So it's a differentiable mapping that's a bijection with a differentiable inverse. Okay, so the idea is that it nicely deforms this region into this region, and so we'll see how that looks when we look at examples. Okay. All right, so that's the very important overlap condition, and it tells you when you have two charts for this set S that are compatible. You can very easily, come up with non-compatible charts. So, so this is a requirement for this compatibility requirement. Okay, good. So now I have a chart, and I know what that means. And if I have two charts that overlap, okay, meaning their domains intersect, then I know what it means for them to be compatible, right? So now what we're going to do is we're going to kludge those two concepts together to define what's called a manifold. All right, so just starting with a set. The set has no structure. Okay, so let me, an atlas. All right, so we had charts, and so when you collect a bunch of charts together, that's called an atlas, which I think agrees with our English language versions of those terms. So let me maybe so we have the sort of regularity R that we're talking about. And so a C R F. Okay, so again, we're always allowing F to be real or complex. So a CRF atlas for S is a collection. All right, so it's a collection of charts. Okay, so U, same font, phi, and let me write that as script U because that's not this. That U, remember that this U is an open subset. Well, it's mapped to an open subset by phi. So this is not to be confused with U phi that we've talked about before. So I'll try to use a different font to distinguish the fact that we always had been calling that a topological vector space, but this one's a neighborhood. Okay. All right. VV, but this VV is a topological vector space. Okay, so this is a collection of charts. Okay, for M, or sorry, for S, such that. Well, we're going to require two conditions, and that. And the conditions will be the obvious ones that you would expect for an atlas. So an atlas should cover the thing that you're talking about. S is equal to the union over phi of the U phis. Okay, so this is the charts cover S. All right, and then the other condition is that every pair of charts is compatible. Sorry. In the sense that we just talked about. They have to satisfy the overlap condition. Okay, so that's what an atlas is. So you just cover your set S with charts, okay, and whenever they intersect, then the overlap condition must be satisfied. So that's an atlas. Okay, so now you say that two atlases, and so let me call an atlas maybe A, like this. That's a script A. All right, so two atlases, A1 and A2 are equivalent if their union is an atlas. Okay. So what does that mean? To be an atlas, two conditions have to be satisfied. The first is that the collection of charts has to cover, well, each of A1 and A2 always covers, so their union will certainly cover S. Um, so really, the condition here is part B. And so I know, of course, because all of the charts from A1 and all of the charts from A2 are themselves satisfy B. Okay, so that means that every pair of charts from A1 satisfies the overlap condition, and every pair of charts from A2 satisfies the overlap condition. And so the only interesting thing is that charts from A1, and when you take them and you pair them with charts from A2, those must satisfy the overlap condition. Okay, so this just means that if, let's say, U V V V is a chart from A1, and if U psi V psi is a chart from A2, then they are compatible with one another. That's the content of the definition of equivalence. Okay, so if you think again, let's think about again just the common English language usage of the words charts and atlases. So this means that if you cover your region with a collection of charts, okay, and each of the charts that you've chosen are compatible with one another, and then I come along and I choose another collection of charts that covers the same region, and mine are all compatible with one another, then when we take our two collections of charts and staple them together in the same book, that the resulting thing is again an atlas. And really, again, that just amounts to your charts and my charts being compatible. Okay. All right, so that's equivalence of atlases. So a differentiable structure for S, and let me say a CR differentiable structure is an equivalence class of atlases with the preceding notion of equivalence. Okay, so really what this means in essence is it just means all possible atlases. And so everything um, that's an atlas and is compatible with one of the atlases in this equivalence class, that's part of this differentiable structure. So this differentiable structure, this equivalence class contains a lot of stuff. It contains every conceivable atlas for S that's compatible with a given one. Okay. Okay, so just the way I've talked about that makes it clear um, that and a differentiable structure, so that's the thing I'm defining is a differentiable structure. So a differentiable structure is fixed once one chooses an atlas. And in practice, this is how we define differentiable structures. We define an atlas. And then once we have an atlas, then you can now consider all possible atlases, which are equivalent to the one that you just defined. And that's what the differentiable structure is. Okay. All right. And then for a manifold, a CR manifold is a set S with a CR differentiable structure, of course. Okay, and we will typically denote, and so you could, sometimes if you want to be really, really fussy and pedantic, you could say that a manifold is a pair, right? So it's an S, let's say a D, right? So S is a set, and D is a differentiable structure. So D is, an equivalence class of atlases. But normally you write a manifold with a single letter, and we'll use letters like M for a manifold. Okay, and so the important thing here that we kind of sweep under the carpet by using just a single letter to denote the manifold is that a manifold is not just the set, it's the set with a differentiable structure. And you can definitely have the same set with different differentiable structures. And again, there'll be a homework problem with that. The homework problem um, as isn't deep, but it turns out there's some deep questions associated with this, which I won't talk about. But there's Fields Medal winning work by John Milner talking about different differentiable structures for the same set. So there's some deep questions there, which we'll just sort of forget they can happen. Right. But in the homework, you'll have some examples of the same set having two different differentiable structures, and the homework questions, of course, will not be Fields Medal winning questions. Okay. Right. So now we know what a manifold is. Let's look at some examples just to see how this works in practice. All right. All right. So if let's say we have a topological vector space V, and an open subset O, write it like this. Right. Um, then O has a natural C infinity manifold structure. Let me say let me write that differently. So it has a natural CR manifold structure for every R. Okay. So how do you do that? Well, the way you build manifolds, according to what I wrote up here, the way you build manifolds is you define differentiable structures. And according to this note, to find a differentiable structure, you need only find an atlas. Right? So what I need to do is I need to find an atlas for this set O. Okay. But the set O has a very natural atlas, namely the whole set itself. All right, so to see this, we only find an atlas for O. Okay, and we can take the atlas with a single chart. Okay, so a chart will consist of three things. Okay, the chart domain, which I had called U, U phi, the locally convex space in which the chart takes its values, which I called V phi, and then the chart map phi. Okay, so I need three things. And so let me write it like this. So U phi, the domain of the chart, is going to be O. Phi is going to be iota O. Okay, so this is a map from O into V. So this is the inclusion map. Okay, and then V phi will be V. Okay, so that's a chart. So let's first just verify that that's a chart. So what do I need for it to be a chart? Well, I need for O to be a subset of O, which it certainly is. I need for V to be a locally convex space, which it certainly is. And then, so the interesting thing is, or the only possibly interesting thing has to do with this chart map. And the chart map in this case is an inclusion. And the requirement to be a chart is that this map has to be a bijection from O onto an open subset of V. Well, that's obviously true because if you take the inclusion of O in V, that's O, its image is O. So this thing is a bijection onto O. So it's essentially the identity map. Okay. All right. So that's a chart. Okay. All right, so then then I should verify that if I take the atlas defined by this single chart, that is an atlas. Well, what do I have to do? I have to verify that the charts from the atlas cover O. Well, that's certainly true because the only chart has domain equal to O. Online, I'm online. Sorry, someone's knocking at my door. Um, uh, um, um, Right. So the charts certainly cover the set O. All right. And then there's the compatibility condition, but there's only one chart. So of course it's compatible with itself. Right. So this is an atlas for O. Okay. And so therefore it defines any other atlas, it defines a collection of charts, any one of which is CR compatible with this one. Okay, so that's how you define the differentiable structure, right? So this is, the way in which you define differential structures is you specify an atlas, right? So that's kind of a boring one. Let's do something a little less boring, but maybe not too much less boring for just for the time being. So let's let M no, sorry, let me not do it that way. Yeah, let's so we had talked about this one before. S1. This is the set of points x, y in R2, so that x squared plus squared is equal to 1. All right. Okay. So I'm going to make this thing into a manifold. Okay. So again, to make it into a manifold, I just have to specify an atlas. Okay. Okay, so I need a collection of charts that covers S, first of all, and then I need to verify that they're compatible with one another. Okay, so there's many different ways you can put charts on this set S1. Unlike the previous example, it's not possible to make this into a manifold by covering it with a single chart. You always need at least two, okay, and you can do it with two, as we will see. And I'm going to give you two different versions of an atlas, okay? So here's two atlases. All right, so and I'm gonna kind of draw these atlases and say what you need to do to verify that they're atlases. One of them is worked out in the course text. The other is not. Right. All right. So I'm going to build two charts for S1. Okay. And all right, so here's S1. It's a circle. Alrighty. And so here, the chart that I build is so this chart is going to take, so it takes the chart domain, first of all, it's going to omit this point. Okay, so the domain U phi1, okay, because there's going to be two charts. Okay, so U phi1 is everything except the point minus 1, 1. Okay, so U phi1 is equal to S1, take away the point 0 minus 1. Okay, and U phi2 is going to be S1, take away, so I have, here I have this point, and I'm going to take away this point. Okay. So it's S1, take away 0, 1. Okay, so the chart domain here is this red thing like so. Okay, omitting that point. And here it's omitting again, point at the top. Okay, so those are my two chart domains. And now I'm not going to write down a formula for the chart maps. I'm just going to, but I will tell you that phi1 is R, Okay, so it needs to be locally convex topological vector space. So here it's going to be a very simple one, R, and similarly here. Okay. And what's the map phi1 going to be? Well, here's how it works. I take a point on the circle in my chart domain U phi1. Okay, so I take any point on the circle except for this point. All right, so maybe let me draw it in blue. Take it back. See how that green looks. All right, so I take a point here. All right, and I draw a line from the North Pole through that point. Okay, and this point right here on the x-axis, okay, so this is the x and the y-axis. Okay, so this point on the x-axis here, that will be phi1 of this point on the circle. Okay, so let me maybe attach some notation to this so that it, all right, so I have a point here, x, y on the circle, right? That's that point. Okay, and this point here on the x-axis, so the x-axis is a copy of r, okay, that is going to be phi1 of x, y. All right, so there's going to be some formula that you can derive explicitly for this point by doing triangle stuff. Okay. All right, and you do a similar thing over here. You take a point on the circle. So let's say this point. Okay, so x, y. I draw a line from now the South Pole through that thing until it hits, sorry, okay, until it hits the x-axis. Okay, and then this point here will be phi2 of x, y. Okay, so that's how you define these two chart maps. All right. Now, so those are my two charts, right? So I have all the data I need. I have all the data I need to define two charts, right? I have a chart domain, I have a locally convex space, and I have a map, right? But now you have to verify the overlap condition. Okay, so to verify the overlap condition, first of all, I would need to write down explicitly what the formulas are for phi1 and phi2, and you can do that, it's not hard. And then you would just use the formula, phi1 inverse composed with phi2, that's the overlap map. Okay, so one can verify explicitly, and it's a fun exercise if you want to do something explicit. You can verify that phi. Okay, so sorry. Before I do that, there's another part of compatibility, and so let me go slowly here. Okay. Right, because compatibility has two parts, right? It has this map needs to be a diffeomorphism, but first I need for these things to be open, right? So the image of the overlap in each of the for each of the charts, those images have to be open. So we can write down what those images are. So one can verify explicitly that phi1 of u phi1 intersect u phi2 is equal to, okay, so let's see what it'll be. Okay. So what will u phi 1 intersect u phi 2 be? Well, that's obviously going to be, so u phi 1 removes that point, u phi 2 removes that point. So u phi 1 intersect u phi 2 will be S1 with both of those points removed. Okay. And then what I'm going to do is I'm going to take the image of, and so that's going to be two little disconnected segments on the circle, right? One going one way and the other one going the other way. Okay, so I'm going to, here, I'm going to take the image of these two disconnected segments on S1 under phi 1. Okay, and what's that going to be? Well, it's going to be everything except I will remove the image of this point because this point's not in U1 intersect U phi 1 intersect U phi 2. But this point under my chart map gets mapped to, so by the process here, I take a line from this point down to, let me make sure I get that right. Oh, sorry, apologies. I take a line from here down to this point, which is omitted. And so what point is being omitted there in the chart? In the image of the chart, it's the point at 0. Okay, so let me write down the answer here. So it's R take away 0. Okay, and the 0 is being taken away here again because I have to remove this point. Okay. All right. I think I think I have to apologize here because I did something stupid. In this chart, I said I removed the point at the South Pole. I don't. I'm very sorry. Sorry, I screwed this up. I apologize. For U phi 1, I remove this point, and for U phi 2, I remove this point. Apologies. Okay, so this point gets, which is what I initially drew, and then I decided I would also remove the other point. All right, so this point gets removed. Sorry, I really messed this up. I'm very sorry. In fact, I messed it up so bad that I think what I'm going to do is I'm just going to start this over again. Sorry about this. It'll be much easier for me to do it over. I'm very sorry. It's a small error, but it's one that's more confusing to try to fix than to just do it from scratch. Okay, but I'll do it a little bit more quickly. All right, sorry about that. Okay, so I have my two copies of S1. You probably saw me making this mistake and you didn't warn me. All right, so here's the North Pole here, and here's the South Pole here. Okay, so U phi 1 is going to be S1, take away the North Pole. So it's going to be 0, 1. And then U phi 2 is going to be S1, take away 0, minus 1. Okay, so let me draw my chart domains again. So U phi 1 is going to be, I remove that point. So it's going to be this thing, like this. Okay, and then this one, I'm going to remove this point. So it's going to be like this. Okay. All right. And the chart maps are just the same as they were before. So, so first of all, the topological vector spaces are going to be the same. Okay. And the maps, the chart maps are going to be exactly what I had before. Okay, so this point is X, Y. Okay, so to find this point, I map to that point there, which is phi 1 of X, Y. All right, and then over here, I take a point, let's say here, X, Y, right? And then sorry, I need to reorient myself to draw something like a straight line. Okay. And so this point will be phi2 of xy in this case. Okay. All right. All right. And so I can write again that phi1 as diagram, phi2 as diagram. Okay. Now I'm sort of where I was before. So I need okay, so I need phi1 of the overlap. Okay, so the overlap will be the same thing that I drew before. The overlap is going to be these two disconnected. So u phi1 and u phi2 intersect in these two disconnected segments of the circle. Okay, and when I take the image of these two disconnected segments from the circle, the only point that's going to be removed is going to be the point that corresponds to the South Pole, because that one's omitted for this chart. Okay, and that will correspond under the chart map to 0, right? So if I take my chart map and I want to find what phi1 of this point is, well, the rule is I draw a line from the North Pole through that point, and I record where it intersects the x-axis, but it intersects the x-axis at 0. Okay, so the point is that phi1 of u phi1 intersect u phi2 is equal to r take away 0. And similarly, phi2 of u phi1 intersect u phi2 is r take away 0. Okay, all right, so over here, I'm omitting this point. And if I take what's the image of that thing under the chart map? Well, I draw a line from here through that point, and it intersects the x-axis at 0. So that's the 0 that I'm removing there. Okay, does that make sense after I fix that up? Okay. All right, so now, so the point is, and I have to verify this, right? So I have to verify according to the definition of compatibility, I have to verify that these are open, and they are. Okay, so those are open subsets of R. Okay, good. And then the thing that I'm not going to do, because you have to write down these things, phi1 and phi2, and I won't do that explicitly. Okay, so it's going to be phi2 composed with phi1 inverse. This is going to be a map from this to this. Okay, but they're both equal to that. And the other overlap map as well. These are of class C infinity R. Okay. All right. So that's one atlas. Okay. Because clearly the union of these two domains, u phi1 and u phi2, if you take their union, that's all of S1. And then I'm claiming here that the overlap maps are C infinity. So that defines so thus have defined a C infinity R differential structure for S1. Okay. And so that's done in some sense. So now S1's an infinitely differentiable manifold, a C infinity manifold. Okay. But just to sort of show that there's more than one way to whatever, stew your goose, whatever you want to say. Let's put another atlas on there. Okay. So again, I will draw my two pictures of S1. Sorry. Okay. So S1. One. And this is maybe the way that you would normally do it. So this might remind you, by the way, these constructions here. If you have a complex analysis course and you studied stereographic projection from the Riemann sphere onto the complex plane, this is rather similar to that. And so these charts are called sometimes stereographic charts. Okay. All right. Okay, so here what we're going to do is we're going to define sort of a normal kind of angle chart for the circle, two of them. All right. So the first one is going to be U V1 is going to be S1, and now I'm going to take away this point. Take away -1, 0. Okay. V, the locally convex space in which the chart map will take its values, is just going to be R. Your perception somehow, of course, is that S1 should be, kind of one-dimensional. So, it's not, but the fact is that this is a choice that you make. And you'll see that clearly on a homework problem. All right. And then what's the chart map going to be? Okay. So the chart map, so I'll draw what this thing looks like. So I'm gonna take a point here, and maybe let me do like I did last time and draw the domain in red. Okay, so the domain omits the point -1, 0. Okay, and then the chart map. Whoop. Okay, so this is going to be a point X, Y. Okay, and then what phi1 of xy is going to be is it's going to be this angle, which I'll call theta 1. Okay, so phi1 of xy is theta, but theta, of course, will depend on xy. Okay, and so theta is going to be some kind of an arctangent function, right? But you have to be a little bit fussy here. And if you're working with examples and you're doing this thing in practice, you have to be careful with how you do this sometimes. So if you just define this thing to be the angle theta to be, let's say, the arctangent of y over x, okay. This has a problem because if you change the sign of both x and y, then this can't distinguish between those points. And so in other words, if you just use that normal arctangent function, this point and this point, which are different points in the chart, are mapped to the same angle, right? So you have to distinguish this. And so you can't really just use the normal arctangent function. So I use this, what I call the smart arctangent function, which takes two arguments, okay? So it takes, and I'll call this theta 1 because I'm going to have a theta 2 here in a second. Okay, and the smart arctangent function just keeps track of not just y over x, but it also keeps track individually of x and y, and so it'll return a well-defined angle as long as x and y, as long as I omit that point. You have to omit some point on the circle, so I'll omit the point -1, 0. Okay, so that's one chart. The other chart, V2 is going to be S1, take away 0, whoops, oops. Okay, take away 1, 0. Okay, so this one will be, I take away this point. So the chart domain is going to be like this. All right. Okay, so V2, of course, will be R. Phi2 of X and Y. Okay, so here, what I will do is I'm going to take a point, which I'll write as X and Y, right? And this one is going to measure, again, it'll be an angle coordinate, and this one is going to be this angle. Theta 2 of X and Y. Okay, will be that angle. All right, so I'm measuring the angle not from the, not from the positive x-axis, but from the negative x-axis. All right, so this is theta 2. Oh, sorry. Theta 2 of X and Y. And now let's express that explicitly using atan. And so that will be, so atan, all right. And so it's going to be minus X minus Y, okay? All right. And the way you can see that it has to be minus X minus Y is this angle here will be the same as this angle here, okay? And this point is minus X minus Y, okay? All right, good. So this is all kind of, elementary, kind of high school, circles and triangles and stuff like that. All right, but it's good to do an elementary example just to convince yourself that you understand what's going on with harder examples. Okay, so I have these two charts now, so I should verify that they're compatible. So V1 of U V1 intersect U V2 is, okay, so V1 again is giving me this angle, whoopsie, giving me this angle, theta 1. Okay, and it's giving me the angle theta 1 for points in this overlap here. So the overlap here omits this point and this point, right? So the overlap omits these 2 points. All right, so phi1 is, theta 1 is going to take all angles between 0 and pi, and then between minus pi and 0. Okay, so this is minus pi 0 union 0 pi. Okay, so it's this union of these two disjoint intervals. And similarly, phi2 u phi1 intersect u phi2 is, okay. All right, so it's going to be the same thing. So it's going to be the angle theta 2 with 4 points on the circle with those 2 points removed. Okay, and so the values of the angle theta 2 will be from 0 to pi, and then from minus pi to 0 again. Okay, now it's relatively easy to write down the overlap map. Okay, so let me write down phi2 composed with phi1 inverse of theta 1. Okay, so theta 1 is going to be taking values in here. Okay, and then I'm going to map it to a point in here. Okay, so let's figure out what it is. Okay, so what this does is it takes the angle theta 1 and basically returns the angle of the same point with angle theta 1, but now in the angle theta 2. Okay, so let's see if we can correctly do what that is. And I very frequently mess this up, but let's see if I can not do that. Okay, all right, so let me take a point which lies from in the region where theta 1 is between 0 and pi. Okay, so that's going to be up here. All right, so I'm going to take a point in this arc of the circle, which will have an angle theta 1 between 0 and pi, and I want to figure out what the angle theta 2 is. Well, the angle theta 2 of this point is going to be it's going to be this angle, right? Because theta 2 is measured from the positive yeah, it's measured from the negative x-axis. Okay, so this is going to be all right, so I need to express theta 2 as a function of theta 1. And so what will it be? It's going to be theta 1 plus, let me make sure I get this right, sorry. Like I said, I very often screw this up. So theta 2 is going to be this angle. So that's going to be oh, right. Okay. So theta 2 is right. Yes. Okay. 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 All right. So it's going to be, so theta 2 is gonna lie in the 0, the minus pi to 0 interval, and so it's going to be theta 1 minus pi. Theta 1 minus pi. Okay, so that is when theta 1 is between 0 and pi. Okay, so let's just double check that that makes sense. Okay, so when theta 1 is equal to pi, okay, so when theta 1 is equal to pi, that corresponds to this point, and so theta 2 at that point should be 0, which it is. Okay, so that makes sense. Okay, good. Now I need to take a point corresponding to angles theta 1, which are down here. So these ones are from minus pi to 0. Okay, and here these angles go from 0 to pi. And so I'm going to take, it should be theta 1, 2 should be theta 1 plus pi, I think. I'll write it down and let's see if it makes sense. All right, so when theta 1 is equal to, sorry, not that. Zero. Okay, so when theta 1 is equal to minus pi, okay, that corresponds to, again, this point here, which is theta 2 equals 0. So minus pi gets 0. Okay, so yeah, it works. All right, so forgive me doing my self-verifications in front of you, but that's what it is. All right, now, is this map a diffeomorphism, right? Well, what is this map? So we can just draw its graph, right? Okay, so we have, let's say, theta 1 here and theta 2 here. Okay, so here's pi, here's minus pi. Okay, so so this thing, when theta is from 0 to pi, it looks like this. The graph looks like this. So remember, I'm omitting these points. Okay, so those points are not included. So the domain of this function is that interval and that interval. Okay, so in this interval, it looks like this. And then here, it looks like this, I guess. Okay, so this is pi. This is minus pi. Okay, does that make sense? All right, so the question is that a diffeomorphism? Well, it's a bijection. Okay, and it's infinitely differentiable, right? So it's not discontinuous because I've excluded that point. And so I'm only interested in how this thing behaves on these two disjoint intervals. And it's just a linear function on each of those intervals. So it's certainly infinitely differentiable. Okay. All right. Okay, good. So this, again, is another way of verifying that the circle, S1, is a infinitely differentiable manifold. So again, we verify that S1 is a C infinity R manifold. Okay. Right, so that was very elementary, and I belabored something which is very simple, but I wanted to really see in practice how these definitions work. Okay. This is not what you typically do in practice. Normally, you'll say something like S1's a manifold, and here's the angle coordinate. But it's good to sort of see how in this very, very simple case, the abstract definitions work out. Okay, good. All right. Let's look at another example. And now, so these two examples that I've looked at have been very well. So this one, sorry. So this one was kind of dull because it had a single chart and a single completely elementary chart, essentially the identity map, which gave you an atlas. Right. So this one's kind of boring for that reason. Okay. This one's kind of boring just because it's, a little bit tedious to write things down explicitly, but it's a very simple elementary example and doesn't contain, and it's finite dimensional, one dimensional. So let's look at something that's a little bit more interesting. All right, so let V be a real vector space. We'll just work in the real case with an inner product. And the inner product, I'm going to write it as G. Okay, so what's an inner product? So an inner product takes two vectors and gives you a real number. Okay, let PG be the corresponding norm. So it's defined using the inner product in the usual way. Take the inner product and apply it to the vector in both slots and take the square root. Okay, and because it's an inner product, G of V comma V will always be positive. Okay. So we talked about this example before, but now we're going to do it carefully. Okay. So we're interested here just because this example can possibly be infinite dimensional. So I've made no assumptions about V being finite dimensional. So if V is finite dimensional, let's say V is n dimensional, then this will be the n-1 dimensional sphere. Okay, so in particular, V is two-dimensional. This will be a circle, right? Which we just talked about. But we want to now think about an example where possibly the thing is infinite dimensional. Okay, and we're going to assume that VG is a Hilbert space. If you haven't seen that word before, and I don't remember if we mentioned the word in this course yet or not. All that means is that V with the norm defined by the inner product is complete. Okay, so a Hilbert space is an inner product space whose corresponding norm space is complete. All right. Okay, so what we're going to do is we're going to make this into a manifold. Okay. All right, so we will define an atlas. For S of V. Okay, and what we're because this thing is possibly infinite dimensional, we're actually going to use a very large number of charts. You can, depending on what your Hilbert space exactly is, you maybe don't have to choose all of these charts, but we're just going to define a chart for each point on the circle. Okay, and I'll draw some pictures to kind of show you what that chart is, and it'll be quite it'll be a similar kind of, the geometry behind this isn't the same as the examples we just looked at, but it's similar. Okay, so let X be a point on this this sphere-like thing. Okay. All right, and I'm going to define a chart. Which I'll call UX, VX, VX, by. Okay, so UX is going to be the set of points, let's say X prime in the sphere thing, so that G of X and X prime is positive. So I'll draw some pictures here in a second, but let me write it down first. Okay. Vx, okay, is going to be, it has to be a locally convex space. And it's going to be the set of points V where the inner product of V with X is equal to 0. Okay, so these are all the vectors orthogonal to X. Okay, and then phi X. And I'll write down the formula and then I'll tell you what that is. Okay. It's going to be X prime minus G of X prime X, X, like that. Okay. All right, so I'm going to draw a picture, and because I'm going to draw a picture, this picture will not be, general enough to really represent what's going on, but it'll give you the intuition you should have in mind for what's going on here. All right, so I'm going to draw like a two-dimensional picture. Of course, everything I've said applies in the case when V is two-dimensional, but it also applies in the case when V is infinite dimensional. Okay, so I have this point X. Why did you do that? Okay. So stop it. So I have this point X. Okay, so X is my point on this sphere thing. All right. So first of all, what's UX? So UX is the set of vectors, the set of points on the sphere thing, whose inner product with X is positive. Okay. And if you think about what inner products are, the way to think about that is I take in this case, it's a line, but in the general case, it'll be a plane through the origin, which is orthogonal to X. So we're also, of course, going to be using that here. Okay. Okay. So this thing here, the dash thing, is also going to be my Vx. Okay. Now, so you want the points in the sphere thing whose inner product with X is positive. So what that means is, so this is the line where of all of the things with inner product 0 with X, okay, and everything on this side will have positive inner product with X, and everything on this side will have negative inner product with X. And so UX is going to be the set of points on the sphere thing where the inner product is positive. Okay, so this is going to be UX. Okay, does that make sense? All right. Now what's phi? So if you think about this for a second, what are we doing? So we have a point x prime. Okay, so x prime is going to be a point in UX, right? It's going to be a point in this segment of the sphere thing on this side of the plane Vx. All right. All right, so what I'm doing is I'm taking what it would, sorry. So first, what's this? So this is the inner product of X and X prime. And the way to think about the inner product of X and X prime is it's measuring the extent to which X prime points in the direction of X. So for example, if X prime is equal to X, then this is equal to 1. And if X prime is orthogonal to X, then this is equal to 0. And so what you're doing is you're taking X prime and you're subtracting away the part of X prime that points in the X direction. Okay, so let me draw a green thing here. All right. So if I take a point, sorry, I meant for that to be green. If I take a point X prime, all right, and I write X prime as two things. So I write X prime as, so I have a component of X prime in the direction of X, and then I have a component of X prime which is orthogonal to X, right? And that's what this is. This is the component of X prime that's orthogonal to X, right? And so when you take this and you take the orthogonal part, that thing there is phi x of X prime. Okay. All right, so basically what I'm doing is I'm taking the chart map takes points in this little region here and projects them down into the plane, which is orthogonal to X. Okay. So that's the geometry of what this thing does. Okay, good. All right. Okay. All right, so those, and so that gives me, for every X, that gives me a chart. Okay, so we should verify that's a chart. So we claim that UX, VX, VX is chart. Okay. All right, so what you have to do to verify that it's a chart is you have to show two things. You have to show that it's a bijection onto its image so that it's injective, okay? And then you also have to show that the image in the topological vector space in which your chart takes its values, that its image is open, okay? All right. Okay, so first of all, okay, so note that the set of points x prime in V, okay, which for which g of x and x prime is greater than 0. Okay, so now I'm not just talking about the points in S, I'm talking about everything out here. Okay, so that's what this is. Okay, this is open. And if you want to really understand why that is, because the mapping x prime maps to g of x prime x is continuous. Okay, so that's true. And if you want to know why that's true because of the Cauchy-Schwarz inequality. So there's a little stuff I'm glossing over here about inner product spaces. Okay. And and the map, which sends x prime in so let me call this set for the time being. Let me call this because yeah, let me call it maybe let me call this u x plus. Okay, and this is the set of points in V whose inner product with x is positive, right? So it makes sense to call that ux plus. Okay. Okay, so now let's take x over okay, so here's a mapping. All right, and so this one, again, this one is defined on all of the points out here, not just the points in the little arc of the circle here. Right? But it's the same mapping. What this mapping does is that it takes a point out here, okay, and a point out here, and it projects it orthogonally onto Vx. Okay, that's what this mapping is. Okay, so this will be in Vx. Okay, so that map is continuous. Okay, and so its image is open. All right. Uh, uh, um, yeah, I shouldn't say, and so its image is open, because that makes it sound like its image is open because it's continuous, and that's not true. So its image is open. In fact, its image is all of Vx. Okay. Okay. So when we restrict it to um, UX, okay, its image will also be open. Okay, and so that's because so again, I'm skipping over some stuff here. So this is the intersection of S with this set. Okay, and therefore that intersection will be an open subset of SX. Okay, and then the chart map is a bijection from this thing onto this, and you have to do a little bit of playing around here, but that will prove that its image is open. Okay, so the image is open. All right, good. And it's also and so I should also say, so we can also verify that Bx from Ux into Vx is injective. Okay. All right, and so again, you can just do this explicitly. All right, so you just take the definition of U, and you take the definition of phi, and just verify injectivity explicitly. So take 2 points in here, um, and show 2 distinct points here, and show that they map to distinct points in here. Just by writing everything down. All right. Okay, so that's a chart. All right. Um, I want to kind of write down the formulas to verify the overlap condition, and that's going to take some time. So maybe what I'll do is I'll stop here for today, and then next time what we'll do is we'll verify that if you have 2 of these charts, okay, labeled by 2 different x's, then there's an overlap condition, and that overlap condition is a diffeomorphism. Right, so that requires a little bit more messing around. So we'll talk about that next time. All right, so we'll finish there for today. Okay, and I'm sorry, I have to run right now. So I should say, it's always the case that if you want to communicate with me, then just contact me. And I specifically am thinking of the homework this week. So there's some elements of the homework that some of you might find a little bit challenging, and I'm more than happy to answer questions about that either by email or we can meet on Zoom. So make sure that if you're having trouble with the homework, that you consult me. Okay. All right, so I have to go, and so I will announce this by email and on the On-Q page, but next week is a week off here at Queen's, and I think at other Ontario universities as well. So I'm going to adhere to the fact that this is supposed to be a forum for students in Ontario, and I'm going to not have any lectures next week. Okay, so we'll see you the week after next week. Bye.